prove this one, again, we're going to start with an identity. And this time, I'm going to divide by, or both sides by cosine squared theta. Because if I look, this piece, I want to turn into 1. Plan. So the obvious thing to do then would be by cosine squared theta. So if I go back and I look at my reciprocal identities, I notice that sine over cosine is equal to tangent. So sine squared theta over cosine squared theta must be theta. Cosine squared theta divided by cosine squared theta is. Look at my reciprocal identities. 1 over cosine is equal to secant. So 1 over cosine squared theta has to equal secant squared theta. And that's what we're looking for. So those are the 3 Pythagorean identities. The next are called the cofunction identities. There's 6 of these. I'm going to write them down, and then we'll justify them kind of just verbally, prove these ones. Oh my. I didn't think this was that scary. So there's those 6. So a little explanation here, or justification as to why this is true. Remember that pi over 2 is the same thing as 90 degrees, right? So 90 minus theta is simply the complement of theta. If you go back and think about our unit circle, if we look at cosine of 30 degrees, that's the same value at like sine of 60 degrees, right? They were 1/2 in each of those locations. Or I should say that's square root 3 over 2, sorry. In either of those locations. That's the idea here. It's just that complementary angles, they're co-function. The all these things like cosine, cotangent, cosecant stands for complementary. So it's like the complementary function to each one of these. Where if you look at the cosine of the complement, it's going to be the same as sine of that angle. Anyways, that's all the justification we're going to give there, is just to justify it that way. When we talked about odd and even beginning, and when we graph sine and cosine and stuff, we mentioned that they were odd or even. So this is just a natural extension of those two ideas. So if you remember, sine was an odd function. That means that a negative sign inside the function can be moved to the outside. And since sine and cosine would be can't, cosine was an even function. That means away. And since secant is the reciprocal, and then if you remember, tangent was sine over cosine, which is like odd over even. Odd over even is still odd. That's the end of our identities for today. We'll do a few examples here now that we're done. I want to point out to you guys that on the content library, there's a sheet called the Basic Trig Identities, where I've kind of consolidated these all into one place for you. So if you wanted to print that out and have it with you while you're working on the assignments, probably makes life a little bit easier than having to flip back through and have them all in one place. So I put this here for you guys so you can use it as you see fit. Okay? So that's there in the content library. I think it'll be quite helpful. Now back to where we had left off. Okay. So let's do some examples where we use some of these identities to solve some. Okay. So here we're asked to find the value of sine theta if tangent theta is equal to 3 and cosine is negative. Now this is a problem that we've already done, right? We did this back in like chapter 2, I think, this kind of a problem where we drew a picture and like used the triangle and the Pythagorean theorem to kind of figure this out. We could do the same thing using our identities. So what I'm going to do is I'm going to use an identity that contains tangent theta and only one other trig function. The one that I'm going to choose is the Pythagorean. No. Go away. I'm going to choose the Pythagorean identity. Tangent squared theta plus 1 is equal to secant squared theta. So tangent, we're told, is 3. So I have 3 squared plus 1 is equal to secant squared theta. So 3 squared plus 1 is 10. I get the square root of 10 is equal to secant theta. Now, since I know that cosine is negative, I also know that secant then would have to be negative. And I know that secant and cosine are reciprocals. So I can say that. Hi, Miss Anderson.
I just get a signature.
I'm sorry, what?
Can I get your signature?
Oh, okay.
Do you want credit for your teaching certificate for the workshop with the nurse? You'll watch the video sometime. Sure.
Okay.
Okay. Two of those kids this morning are quarantined.
They weren't on the Zoom call at 7:45 when I took attendance.
Are they not?
I don't remember some of them are, some of them weren't.
Okay, so if they weren't, that's what Jim wanted to know. So if they weren't on the Zoom, they put it in that. Perfect. That's perfect.
At the start of the class.
Perfect.
So if they came late, I don't change anything.
Okay, that's perfect. That's all.
Okay. You're welcome. Elizabeth? Okay. Why would I need to do that? Well, this is why I'm going to do that. Because I know that tangent theta is also sine over cosine. So to answer the question, or to relate tangent to sine, which is the kind of the two pieces of information I had, I also need to know what cosine is. Right? Because we're trying to find sine theta. Is that okay? So that's what I'm about to fill in now. So I'm going to multiply both sides by cosine theta. And now I can say square root of 10 times 3 is equal to sine theta. Or that. Probably wouldn't leave that as our final answer, though. What's wrong with this? Yeah, we have that square root in the denominator. So we'll multiply the top and bottom by the square root of 10. And that's probably what we would leave as our final answer. Elizabeth? Sure. And that's about as hard as that type of problem gets. Some of them would be more straightforward than that, where you might not have to use 2 or 3 identities in combination to get that to work. Let's do a different kind of problem. So let's say we have sine cubed x plus x times cosine squared x. We're asked to simplify this expression. So what do we mean by simplify? Well, we want to make something that involves less terms. So right now I have 2 things that are being added together. A simpler expression would probably be 1 thing added together. And I have 2 different kinds of trig functions going on. Simpler would mean I'd have maybe 1 or no trig functions going on. Maybe it can reduce down to a single constant or something. But that's what I mean by simplify. So I want to make this have less terms or less trig functions involved. My tools to do that are basic algebra things, so like factoring or foiling or distributing, like things like that we can do. Or my other tool is my identities. Okay with that plan? So if we look at this, sine cubed plus sine squared times cosine squared, typically what I would do is I would first start to see if there's any obvious algebra thing that I could do here. Do you guys see any obvious algebra thing to do here? Great. So we could factor out a sine x, right? And that's an improvement because it turns this from an addition problem that has two terms into a multiplication problem with two factors. And that's a little bit simpler. So that's kind of heading in the right direction, typically. Okay, that's probably it as far as algebra things go. Let's look for identity things. So there's one in particular that should be flashing and standing out here as a good identity to use. Jason? Yeah, that's equal to 1. And then obviously sine times 1 is just sine, and that's as good as we can do. That's down to a single trig function. We're finished. Is everybody okay with that? Now I want to say for the record on problems like this, it is really important that you're showing your work. Okay? On a test or a quiz, if you just write this equals sine, I'm not giving you any points for this. You have to show some clear and logical work and how you've moved from one step to the next step to demonstrate how you're getting there. Keith.
Can you give a list of the
Identities?
Yeah.
So for this chapter, I believe on the test I will give you the identities. That kind of goes away by the time the next test rolls around because you're going to get a new set of identities. So these older ones are going to be ones that you need to know, and you'll get a new set going on. But these ones that we've called on the basic list eventually become ones that kind of the expectation is that you have committed to memory at some point. Not a requirement for the first test on involving these, but eventually that becomes an expectation that just like you have these things memorized. Is that what you needed?
Yeah.
Sound reasonable? Okay. Let's look at another one. Okay. So here we have secant x minus 1 times secant x plus 1 all over sine squared. Any ideas on what to do first here? So I am intentionally waiting to get people's suggestion because I think these kinds of problems, there's often we always do this first, you always do that first. And you need to develop a little bit of intuition. So you need to just like guess at what to do and make suggestions about like, maybe I think I'd do this. And I'll tell you whether I think it's a good idea or bad idea to help develop some of that intuition. Because I think it's hard at the start to know what to do on these kinds of problems. So it's okay to suggest things that are like, well, yeah, I don't know, and I'll tell you why I think it's a bad idea or a good idea, or well, sometimes I'll be like, well, I don't know, I wouldn't have thought to do that, let's see what happens. Elizabeth, I think that's a great idea. So if we look at this, there's no obvious trig identity to apply, right? So the only algebraic thing that we could try to do would be to FOIL it out. And I noticed that that was just a difference of 2 squares factoring pattern, so I just used that to FOIL it out really quickly in my head. Certainly you could, you know, to do the real FOIL and like you'd end up with the same spot, but I just wanted to point out why I did it so quickly without having to write anything extra down. Jason. So you can't square root the top and bottom of this because say like we had the fraction 5 over 2, you can't just like do that to 5 over 2 and have it still equal 5 over 2. If this was an equation, you could take the square root of both sides. That would be okay, but we don't have an equation, we have an expression. So that's, but it's, you're thinking in the right fashion, right? Like trying to get something to cancel out. Keaton. Okay, so Keaton says, should we change secant? Oh, okay. Yeah, so he says we can take the Pythagorean identity, tan squared plus 1. If I subtract 1 from both sides of that, I have the numerator in the fraction that we're looking at. Does everybody see that? So we can, x is the variable we're using. Jason. Okay? I see, Keaton. I'm just giving everybody a chance to process what's going on here and think about what to do next, since it seems like you already have a good idea of what's going on and what to do next. And that's okay. Jason. Yeah, so we think about this as tangent times 1 over sine squared. And that does cancel the sine squareds. This is what you were going to suggest also, Keaton, right?
Yeah.
Okay. Same to it, right? Yeah. Good. Excellent. Elizabeth. So we thought about this as tangent squared times 1 over sine squared, right? That's still the same thing. Because tangent was we turned it into a fraction. It made it easier to think about that as the multiplication of 2 fractions rather than fraction divided by fraction. You know what I mean? So I just thought about that way because it made the algebra a little bit more convenient to see what to do. And then my last step here would be to squared. Yes, perfect. And that's down to a single trig function. That's as good as we can do. Ooh. Let's do another. Jason, you got an idea? So cross multiplying is a solving technique. If that subtraction symbol is an equal sign, then yes, you could do that. But since it's a subtraction symbol, cross multiplying is not appropriate for this situation. But again, like, it's a good idea. It's something that you often do when you have two fractions like that, but you need an equal sign between the two fractions to apply cross multiplication. Elizabeth? Okay. So, yeah, so Elizabeth wants to turn this into tangent, right? That's what you're saying? You could. I would not. Okay? So, not that it's wrong, what you're saying, but I don't think it's going to get us in the right direction. The reason I say that is because the other piece is still a fraction, and there's nothing that we can do trig identity-wise to that fraction. So we'd still then have a fraction and then not a fraction. To combine them together, you're going to have to make a common denominator, which doesn't help. You know, like, that being tangent doesn't make that any easier than if it was not tangent like it is right now. So I would probably just leave it the way it is and not turn that into a tangent. It's not wrong to do it. I just don't think it's going to be helpful for this particular problem. Does that make sense as to why?
Yeah.
Keaton? So if it was an equation, yes, but this is just like a number. So like if I have like 1/2 minus 3/4, I can't just square the whole thing and have it still be the same number, right? So we can't do that. If it was an equation that had two sides to it, yes, you can square both sides. That would be okay to do. But this is just an expression, so we can't do that. So you could if it was 1 minus sine squared, because it's 1 minus sine, we cannot. Here's my suggestion to you. Let's make a common denominator and subtract these two fractions. That's what I would want to do as my first step. Abigail. Of course. So to make a common denominator, what do we have to multiply the first fraction by? Cosine over cosine. And what do I have to multiply the second fraction by? Not sine over sine. 1 minus sine over 1 minus sine. And just as something I want you guys to be kind of careful about, when you guys are talking, you're not including the variables. Like you're just saying 1 over sine or whatever, which is fine when we're talking. Please make sure you're writing the variables when you write down on your sheet of paper. Like, I will be picky about that when grading things. So if you just drop your variables at one point, like I am going to make a deduction on doing that. Okay? So just to be clear and be honest and upfront about what's going on. Like when we're having a conversation like this, it's no big deal. I know what you mean. But once you start writing it down, it's like, well, you're saying this is equal to that, and that's not true because that's like saying square root of 2 is equal to square root. It's like, well, no, that's nonsense. So like the notation there matters when you start writing it down more so than when we're speaking. Okay. Anyways, moving forward, so we have cosine squared theta minus, and let's just do this, right? Is everybody okay with why this turned into a plus sign? Well, it's because I had really minus sine x times 1 minus sine x is really what that was, right? So when I distributed the negative sign through, the sign changed on me. Is everybody okay with seeing that now? So I wrote it down, and then I thought to myself, it's like, I bet at least a couple people missed why that sign flipped. I better make sure I point that out, because it's an easy mistake to make, right? When you have a negative sign in front of a quantity, it's easy to forget to distribute with the negative sign, especially when we have, you know, the negative sign hanging out here and then we're distributing from over here, right? Very easy to make that mistake. So I thought I better slow down and point that out. Everybody's clear, though, as to what I did and why we had to do that? Okay. All right. What do you see now? Keaton? So cosine squared would be 1 over secant squared, but I don't think that's going to help us.
Oh no, I mean like sorry, I meant
Okay. So what are you wanting to do with the Pythagorean?
like 1 minus sine squared.
Okay, you could do that, but can I point out to you that we have a cosine squared and we have a sine squared,
Oh,
and there's addition in front of each of them.
yeah, I guess.
So that would be even easier to use, right? Not what you're saying is wrong. You would have ended up in the same place, but it's like an extra step that we don't need to do.
Yeah.
Since you're using the same identity that I'd be using here, it's just kind of cutting out a step. Is that okay with everybody? And notice that because these are both positive, that's fine, right? If this was still a negative sign, we could not do what we were about to do. But it's okay. Oops. Keaton. Yeah. Great. Out the 1 minus sine x's, and what's that going to leave me with? Close. 1 over cosine x. Yep. So again, I was careful there in asking like what I was going to be left with, because again, that's a common mistake I see students make when they reduce a fraction like that and the numerator goes away. Sometimes we'll write just the denominator instead of 1 over the denominator, and that's a common mistake, and I just wanted to make sure we point that out because I don't want you to do that, right? And then my last step would be to, yeah, we'll just turn that into secant. Elizabeth? Yes.
What do you do with
Why do I give them to you on these?
the identity?
Why would I give you the unit circle on that test?
Yeah.
Well, you're gonna find out in the next section when we're starting to do some more harder solving problems. Basically, my answer is you'll see. Okay. All right. So let's take a look at another. We'll do one more after this one, and then we'll call it good for today. Take a minute and look. I'm going to come back to you. I'm just going to pause here for a minute and let everybody take a look, because I just wrote it down a second ago, and I see people flipping around to look for identities on what they're going to go, but I'm going to go to you first. Okay, what do you got? What do you suggest here?
You change that to negative.
Great. So we can use our odd-even identity to turn that into negative cosecant. Great. And then I'll just rewrite it that way because it's a little bit nicer. Everybody's okay with that? I can just move the negative sign all the way out front since everything is just being multiplied together. It's okay to do that. What do you want to do next? Jason? Great. That's what I would do. And what happens here? Those cancel out, right? And we're left with -1. That was quick. Oh, okay, Elizabeth, what do you suggest? Yeah, so that's exactly what I would do first. Because I would do that. Great. And that's important because we want all the variables to be the same thing inside the trig functions, right? Now everything just has a y inside of the trig function. So we can combine these things and cancel these things if we have the opportunity to. We couldn't until we got all the variables to be the same on the inside, right? Everybody's okay with that idea? Good. What next? Okay, you want to distribute the sign through? Sure, that's fine. At some point that's applied through, might as well do it now, I suppose. Keaton? Okay. So what we did here, it seems like it might have made it worse, right? In general, though, this is a decent idea, is to turn everything in terms of sines and cosines, because it makes combining things much easier once we've done that. And usually good things eventually can happen. It's usually easier to work with everything in terms of sines and cosines than having some of these quotient or reciprocal identities going on. Or reciprocal functions, excuse me, or quotient functions going on. Typically will make things a little bit easier. Elizabeth. So like, you're saying that? If they were multiplied together, yes. But they're being added, so no. We can cancel the signs as I've drawn there, but that's it. Is that okay? What can we do with that other piece, the sine times sine over cosine? Keaton? So yeah, I would say not yet, but we can multiply those two fractions together to make sine squared. And then if you wanted to do what you're suggesting, Keaton, then it would be okay to do that, but we don't have a sine squared yet to turn it into a 1 minus cosine squared. You know what I'm saying? But I don't think that that's probably the route that we want to go now that we have it written in this form. Kristen? Of course. Elizabeth? That's what I would want to do here. Yes. So that's good. The only way that we're going to get these two terms, we have two separate things added together, into one term is by making a common denominator and adding these two fractions. So let's do that. So I have to multiply the first piece by just cosine over cosine. So there's my single fraction now. Elizabeth? Absolutely. Sine squared plus cosine squared is equal to 1. That's one of our Pythagoreans. Elizabeth? Yep. That's as good as we can do. We're down to a single trig function. Lovely. Okay. So you guys should be able to do 1 through 14 from the homework set at this point. We'll do some additional practice. We have some worksheets from this section also, but let's start here with this. And you guys can spend the rest of your time today kind of getting started on this homework, or if you have questions in preparation for the Monday's test, you could ask me about those sorts of things individually too if you wanted to do that. Okay? Thanks. I think you guys did a good job today on